All right, let's dive into something that sounds like it's straight out of science fiction. We're talking about smashing together two of the most powerful, most hyped technologies on the planet, quantum physics and machine learning. Now, the promise here is, well, revolutionary, but the reality? It's a lot more complicated. So today, we're going to try to separate the real science from the hype. So, yeah, what actually happens when you take the two biggest buzzwords in all of tech and smash them together? You get a whole lot of noise, that's for sure. Our job here is to cut through all of that and figure out if quantum machine learning is really the next giant leap for humanity, or if it's just a really powerful combination of hype. Okay, so let's start with the exciting part, the promise. To really get why people are so excited, we first need to get a handle on what quantum machine learning, or QML, even is. At its heart, QML is all about using the totally weird and wonderful rules of quantum mechanics to give machine learning a massive upgrade. The key thing to get is that it's not about some new kind of quantum data. Nope. It's about taking the same old classical data we have right now, pictures, text, numbers, and analyzing it in a completely new and hopefully much more powerful way using a quantum computer. So why all the buzz? What's the big deal? Well, it all comes down to a fundamental, mind-bending difference in how quantum computers actually process information. You gotta think of it less like a faster version of your laptop and more like a computer that plays by a completely different set of rules for reality itself. So the computer you're watching this on uses bits. They're just tiny switches that are either on or off, a 0 or a 1. Simple. But a quantum computer? It uses qubits. And thanks to this wild quantum principle called superposition, a qubit can be a 0, a 1, or, and this is the magic trick, both at the same time. That ability to exist in multiple states at once is the whole game. It lets you represent information in an exponentially more powerful way. And the scale of this is it's kind of hard to wrap your head around. With just a few hundred qubits, you could theoretically represent more values than there are atoms in the entire known universe. So the idea is, by encoding data into these incredibly dense quantum states, QML algorithms could just blaze through problems at a speed that is literally unimaginable for any classical computer we could ever build. And look, this isn't just some vague promise of going faster. Researchers have already pinpointed specific, really hard problems where this quantum approach could be a total game changer. We're talking about things like solving massively complex financial models in a blink, or sifting through gigantic databases to discover new drugs. These are the kinds of world-changing applications that people are dreaming about. Now, to try and make sense of this whole new world, researchers have kind of broken the field down into 4 main roads you can take. It really just depends on 2 things. Is your data classical or quantum? And is your computer classical or quantum? This little chart actually makes it all super clear. In the bottom left, you've got standard machine learning, classical data, classical computer. That's what we do now. Way over on the other side, you've got this super futuristic, fully quantum world, processing quantum data on a quantum computer. But see that top right box? That's where all the action and all the hype is right now. QAI, taking our normal classical data and figuring out how to crunch it on a quantum computer. That's the dream of quantum-enhanced AI. But, and this is a huge but, this is where the story hits a major snag. You see, building these QML algorithms isn't just a hardware problem of building better quantum computers. Turns out there's this massive fundamental math problem that's become a huge headache for the entire field. And here it is. It's called the Barron Plateau. The best analogy is this. Training a machine learning model is kind of like trying to find the lowest point in a huge, hilly landscape. The Barron Plateau is what happens when, as you make your quantum model bigger by adding more qubits, that entire landscape becomes almost perfectly exponentially flat. The algorithm literally can't tell which way is downhill, so it just gets stuck. It can't learn. And that's a massive barrier to scaling these things up. So this huge theoretical problem, plus all the insane practical challenges of just building these computers, has led many of the top researchers, the pioneers in QML, to kind of tap the brakes on all the hype and just ask for a healthy dose of realism. And you hear it directly from the experts. Maria Schultz, who's a huge name in the space, puts it perfectly. She says, basically, we haven't done our homework yet. This field is brand new. We're still figuring out the absolute basics, not engineering practical tools for tomorrow. And man, this quote from Jacob Viamonte just nails it. He says, when you mix machine learning with quantum, you create a hype condensate. I mean, that's just a brilliant way of saying we've taken two incredibly exciting, buzzworthy ideas, and the result is a level of expectation that has just skyrocketed way, way beyond where the actual science is today. And this might be the most sobering reality check of them all. Physicist Ryan Swake just lays it out there. He says, flat out, that he hasn't seen a single shred of evidence of a real-world task where it would actually make sense to use a quantum computer instead of a classical one. That killer app everyone is looking for, it's still missing in action. So, after weighing this incredible, world-changing promise against these really serious, fundamental problems, where does that leave us? Are we talking revolution? Or are we just talking hype? The bottom line is this. Right now, QML is an absolutely fascinating, super important area of theoretical research. It's pushing the limits of what we know about physics and computation. But, and this is the key thing, it is not a practical technology that's just around the corner. The road from a brilliant idea in a lab to a tool you can actually use is still very, very long, and honestly, very uncertain. And really, that leaves us with the ultimate question, doesn't it? Is this barren plateau problem a dead end, an insurmountable wall? Or is it just a really tall mountain that we haven't figured out how to climb yet? Is quantum machine learning destined to just live in physics textbooks? Or are we sitting here, right now, witnessing the very slow, very difficult birth of a technology that will truly change, well, everything? For now, that answer is still being written.